Hello students, welcome to part 7 of the chapter Electrochemistry. In the last part we were discussing about various properties of conductors. There were two types of conductors, electronic conductor and electrolytic conductor, and one such property was conductivity. In the case of electronic conductor, we have a relationship like this: conductance is equal to conductivity into A by L. This relationship we saw in the last part, and while defining conductivity is nothing but a conductance when area of cross section is unity and length is also unity. So G is equal to conductivity. Conductance is equal to, so conductivity is defined as conductance of an electronic conductor whose area of cross section is unity and length is also unity. In this way you can compare the conductivity of different materials to see or to evaluate their relative conductivity. In the case of electrolytic conductor, we had a conductivity cell in order to calculate the conductivity that had two platinum electrodes. So in the case of electrolytic conductor, you can define in the same way, where it is the conductance of an electrolytic solution whose platinum electrode are separated by a distance of unit length and whose area of cross section is also unity. So if that is the case, then conductivity is its conductance. So let's see the definition of conductivity of electrolytic solution. Definition is conductivity of a solution of any concentration. So you can take electrolyte of any concentration is the conductance or conductivity. So conductance is of any concentration is the conductance G of 1 unit volume. Why it is called 1 unit volume? Because two platinum electrodes that we saw in the last slide were at a distance of unit length and have a unit of area of cross section. So both are unity. Two platinum electrodes are separated by unit length and have an area of cross section that is of unity. If that is the case, then length into breadth into height all are unity, then it is called unit volume. So conductivity is the conductance of unit volume. This is a very important term that we have to keep in mind in this part. That is, conductivity is nothing but conductance of unit volume. But what is the problem here is, between electronic conductor and electrolytic conductor there is one major difference. In electronic conductor, with the conductance, concentration will not vary, whereas in the electrolytic conductor concentration might vary, but conductivity is not mentioning that. Conductivity is just mentioning about length and area of cross section, nothing else. Conductivity is equal to conductance when unit length or length is unity and area of cross section is also unity. It is nothing mentioning about concentration. So it is essential, while expressing conductivity we should also mention the concentration. So expression of conductivity varies and is not varies expression of conductivity varies and does not have concentration term inside it. So conductivity or kappa is divided by molar concentration to incorporate the concentration term. So in order to express the concentration term, what we are going to do is we are dividing conductivity with molar concentration. So conductivity is divided by molar concentration. What is molar concentration? Concentration of an electrolyte solution expressed in number of moles per unit length, unit volume, per unit volume. So conductivity is nothing but molar concentration is nothing but number of moles of electrolyte in a solution in unit volume. If you divide this If you divide conductivity with this molar concentration, then it is called molar conductivity. It is called molar conductivity, and it is expressed using the symbol lambda m. This lambda is uppercase or capital lambda in Greek alphabet. In Greek alphabet, like in English, they have uppercase and lowercase, capital letter and small letter. So we have seen the lowercase lambda, especially that symbol is used for wavelength. It is also used for various other purposes, but the main purpose which you have seen is using small lambda or lowercase lambda as a symbol to represent wavelength. Here molar conductivity is expressed using uppercase lambda with a subscript of m to show that it is molar conductivity. So molar conductivity lambda m is equal to conductivity divided by C. So what is conductivity? Again, conductivity is the conductance of unit volume of solution. So conductivity is the conductance of unit volume of the solution. And when you divide it by C, you are dividing it with molar concentration. Let us see an example. What actually a molar conductivity is. For a solution, conductivity is 0.25 Siemens meter is to minus 1. What does this mean? Conductivity is the conductance of one unit volume of solution. So if there is a unit volume of solution, the conductance of that unit volume is called conductivity. And that unit volume has 20 mole per meter cube. Per meter cube means it's the unit volume. Length into breadth into height. Meter cube. So in one unit volume, there are 20 moles of the electrolyte. And for that unit volume, what is the conductivity? Conductivity is 0.25 Siemens meter is to minus 1. So this is the meaning of both these terms. What is lambda m? So by the formula that we have learned, lambda m is equal to K by C. That is conductivity divided by 20 mole per meter. Then that is equal to 0. What does this mean? So I have conductivity of unit volume, and in that unit volume there is 20 mole. So if your entire screen is unit volume, and that unit volume has 20 mole inside it, your entire screen, imagine that your entire screen of the video is unit volume meter cube here, and it has 20 mole inside it, and that entire unit volume has a conductivity of 0.25 Siemens meter is to minus 1. The entire unit volume has a conductivity of this. What I am doing is that conductivity divided by 20 mole. So I am dividing with 20. Why 20? Because it is the number of moles. When I divide by 20, I am getting a result. What is it? It is nothing but conductivity of 1 mole. So if there is 20 mole inside it, I can divide this screen into 20 parts. Let's say this is one part, and this part will contain 1 mole, and this is called molar volume. So the entire unit volume is this screen, and molar volume is the volume that contains 1 mole of electrolyte. So I am dividing conductivity with 20 mole. That means now I have the conductivity of 1 mole. I have conductivity of 1 mole, and it is called molar conductivity. So what is molar conductivity? Molar conductivity is nothing but conductivity of 1 mole electrolyte. Conductivity of 1 mole electrolyte, or you can say molar conductivity is the conductivity of molar volume. What is molar volume? Volume that contains 1 mole of electrolyte. Let us again try to highlight the important things that we have to see here. Conductivity is conductance of unit volume. Unit volume means, as I said in the example, it is the entire screen. whereas molar conductivity is conductivity of molar volume. Molar volume, that you have to divide the entire volume by number of moles, then you will get the molar volume. So the difference is conductivity is about conductivity of unit volume, whereas molar conductivity is the conductivity of molar volume. Since we have molar volume and conductivity inside the same relationship, now we can say that conductivity is also expressing concentration inside it. So now we have a complete meaning of all the different variables present inside this electrolytic solution. Earlier, if you are mentioning only conductivity, there is no concentration term. Now here we have a concentration term. So without concentration term, if you are just saying that about this unit volume, you are not mentioning how much electrolyte is inside, all this stuff. Whereas if you are mentioning about 1 mole, then you are mentioning the concentration. Clear, I guess. Now again, what is the definition? Definition is molar conductivity of a solution at a given concentration is the conductance of molar volume. What is molar volume? Volume of solution containing 1 mole of electrolyte kept between 2 electrodes. Now we have the conductivity cell and has 2 platinum electrodes with an area of cross section A and distance of unit length. That means the platinum electrodes must be kept at a distance of unit length. So the distance between the platinum electrodes is defined as unit length, whereas area of cross section is not defined, because if you define area of cross section as unity, then it is unit volume. Molar conductivity is not about unit volume, but it is about molar volume. So distance, though it is defined as unit length, area of cross section might vary because it's for molar volume. If you fix this also, then it will be unit volume, so you won't fix this. Okay, now again our formula, lambda m is equal to kappa divided by C, and C is number of moles per unit volume. C is equal to number of its molar concentration, so it is number of moles per unit volume. In the earlier problem we saw that it is 20 moles per meter cube. 20 moles, that is number of moles, meter cube is the unit volume, is number of moles per unit volume. So you can substitute for C in this equation. We get lambda m is equal to kappa divided by n divided by v. Therefore v will go to the numerator, that is lambda m is equal to kappa into v divided by n. What is v here? This is the unit volume. If n is 1 mole, if it is 1 mole, then you can write the equation as lambda m is equal to kappa into v. So v here is unit volume. So again, molar concentration is number of moles divided by volume. Volume means what? Length into breadth into height, that is, it is cube of length, mole divided by length cube. In the case of conductivity cell, or electrolytic solution, volume's unit is generally expressed either as meter cube, centimeter cube, or decimeter cube. Volume is generally expressed as meter cube, centimeter cube, or decimeter cube. What is decimeter cube? Decimeter cube is liter. 1 decimeter cube means liter, whereas meter cube and centimeter cube are different. Decimeter cube is different, it is liter, whereas meter cube and centimeter cube are different from liter. Normally in chemistry, concentration of a solution is expressed in molarity. And what is the unit of molarity? Mole per liter. Concentration of a solution is generally expressed in chemistry in the form of molarity. Molarity means mole per liter. That means mole per decimeter cube, because 1 liter is equal to 1 decimeter cube. So if it is given in liter or decimeter cube, then fine. But in most of the cases, unit volume is generally expressed in either meter or in centimeter. So that means we have to convert our molarity, or we have to convert C in terms of molarity. We have to express this C, the factor C, mole per length cube, in terms of molarity. Let's see how. If V is in meter cube, what does this mean? So I have a container that has a unit of unit volume of 1 meter cube. 1 meter cube contains 1000 liters. 1 meter cube contains 1000 liters. What is molarity? Molarity is mole in 1 liter. How many liter does this 1 meter cube have? It has 1000 liters. So if you look into this entire area of 1 meter cube, 1 mole per liter is just a small area here. This is 1 liter. The entire area has 1000 such liters. So if 1 liter has, say, X mole, that is molarity. Molarity is number of moles per liter in 1 liter. If it has, let us say, X moles here in this 1 liter, then how many moles will be there in 1000 liter? There is 1000 liter. I am just taking only a small portion out of it, that is 1 liter, and it has X moles. Then how much moles are present in this entire 1000 liter? It will be 1000 into X moles per 1000 liter, isn't it? 1000, that means if 1 liter contains X moles, then 1000 liter contains 1000 into X, or 1000 into molarity. That means if C is expressed in mole per meter cube, but the concentration of the solution is given in molarity, then how can express this molarity in meter cube? It is like this. C is equal to, you just multiply this molarity given in mole per liter cube into 1000. This is the reason for that, because if the concentration is given in mole per liter, 1 meter cube contains 1000 liters. That means I have to multiply this with 1000 to convert it into 1 meter cube. So C is equal to concentration, concentration or molar concentration C is equal to molarity into 1000. Let us take the unit of one of all these. So if this unit is mole per meter cube, molarity as we know it is mole per liter, and 1000, why we added at 1000 here, multiplied with 1000 here? Because it is 1000 liter per meter cube. 1 meter cube contains 1000 liters. This is the unit of this 1000. So if you try to simplify this, liter and liter, one is denominator, one is numerator. Denominator here and numerator here, they will cancel out. Then it will be mole per meter cube. Then we will get the unit here. Okay, so lambda m is equal to, say, molar conductivity is equal to conductivity divided by C, where C is mole per meter cube. It can be substituted with molarity into 1000. That is substituted with kappa divided by molarity into 1000. 1000 is 10 raised to 3. So lambda m is equal to kappa divided by molarity into 10 raised to 3. If the concentration is given in terms of meter cube, you don't have to worry about it. Then you just substitute here for that value. But if the concentration is given in molarity, then you have to use this formula. Okay, this is how when volume is supplied in meter cube. What if it is supplied in centimeter cube? If V is in centimeter cube. Now I have a container here. This is just 1 liter. That means it is expressed in molarity, number of moles in 1 liter. This is molarity. What is molarity? Number of moles in 1 liter volume. This is molarity. 1 centimeter cube means it is only a small part of this molarity. 1 centimeter cube is small part of this 1 liter, and 1000 such centimeter cube makes 1 liter. 1 liter is equal to 1000 centimeter cube. Generally, our concentration is given in molarity. In chemistry, solution is given in molarity. But if they are asking for centimeter cube, I have to convert molarity into or centimeter cube. I have to express molarity in terms of centimeter cube. That means if molarity is given, if I want to convert it into centimeter cube, I have to divide molarity by 1000. That is, C is equal to molarity divided by 1000. Because centimeter cube is only a small portion, 1 by 1000th portion of a molarity. So I have to divide molarity by 1000. Or you can write molarity into 10 raised to minus 3. Molarity by 10 raised to 3. If it goes up, then it molarity into 10 raised to minus 3. Again, if I am looking to the units, mole per centimeter cube, molarity is mole per liter, 1000 is centimeter cube by liter. That is, 1 liter contains 1000 centimeter cube. 1000 centimeter cube per liter in 1 liter. If you cancel out liter and liter, then it is mole per centimeter, which is the value of C. So I can substitute if volume is provided, or if the length is in centimeter here in this entire equation, then the concentration is applied in molarity, then K by C must be written like this: K divided by molarity into 10 raised to minus 3, because C is equal to molarity into 10 raised to minus 3. So again, if I am repeating, if unit of length is in meter, when you go for the calculation of lambda m, then you should use this equation, kappa divided by 10 raised to 3 into molarity. On the other case, if the length is in centimeter, lambda m is equal to kappa divided by 10 raised to minus 3 into molarity. So centimeter and meter have the same equation. Only difference is 10 raised to 3 is in meter and 10 raised to minus 3 is in centimeter. Even if they are asked for centimeter, you can go for this equation. Then at the end you have to convert it into centimeter. And if you are using in centimeter, if the question is in meter, you can go for this equation, but in the end you can convert it into meter. How? This is possible by the interconversion using this one. So 1 Siemens meter square mole raised to minus 1 is equal to 10 raised to 4 Siemens centimeter square mole raised to minus 1 Siemens. So interconversion is possible using this unit. We will look into an example. Convert lambda m value 12 Siemens meter square mole raised to minus 1. So here it is meter to centimeter scale. What is supplied? It is meter that is supplied. This unit in meter is equal to 10 raised to 4 unit in centimeter. So 12 means what I have to do? 12 into, I have to multiply with this. That is 12 into 10 raised to 4 S. So I can convert this from meter to centimeter. And if I am using this, I can convert centimeter to meter. So interconversion is also possible. Let's look into a problem. For a conductivity cell, there is a conductivity cell and its resistance, and the conductivity cell contains 0.1 molar KCl solution. Its resistance is 100 ohm. R is 100 ohm. So for the conductivity cell with 0.1 molar KCl solution, its resistance is 100 ohm. On the other hand, there is another solution, 0.02 molar KCl solution, resistance is 520 ohm. So we have two solutions, 0.1 molar KCl and 0.02 molar KCl, dilute solution. For this solution it is 100 ohm, and for this 0.02 mole KCl it is 520 ohm. Calculate conductivity. I have to calculate K. N molar conductivity of, I have to calculate kappa and lambda m for 0.02 molar KCl solution. And they have provided that conductivity kappa of 0.1 mole per liter KCl solution is 1.29 Siemens meter raised to minus 1. So in one case, for one solution they have provided with the conductivity kappa value. The other one we have to find out the kappa value and molar conductivity. In both cases I have R values. So first what we have to do is let the 0.1 molar KCl solution be 1 and let 0.02 molar KCl solution be 2. We are treating both solutions as 1 and 2. Molarity in the case of first solution is 0.1 molar and in the second case it is 0.02 molar. Resistance is 100 ohm in the first case and the second case 520. K1 in the first case is 1.29 and the second case we have to calculate it, and for lambda m in the second case also we have to calculate it. So in this case we know the resistance and we know conductivity. If resistance and conductivity is known, we can find out the cell constant. Using the cell constant I can find out conductivity of the second solution, because cell constant is a constant for all type of solution, because it's of a conductivity cell. So cell constant is G star into RK. We have learned this in the last part. G star means cell constant is equal to resistance into conductivity. Since G star is a constant, R1 K1, this into this one, so product of the first two will be equal to the product of second two, R2 into K2, because G star is a constant. G star is equal to R into K, that is R1 into K1 will be equal to R2 into K2. From this, K2 is equal to R1 K1 divided by R2, that is equal to 100 into 1.29 divided by 520. 100 is from R1, 1.29 its first solution conductivity divided by 520, and I got K2 as 0.25 Siemens meter raised to minus 1. So now if I have the conductivity, how I will calculate molar conductivity? Molar conductivity is kappa divided by C. C, here kappa is in meter. That means I should go for the equation, because here it is given molarity. Molarity is given. So if I want to convert it into meter cube, what equation should I use? Lambda m2 is equal to K2 by C2. K2 means second solution with its molar concentration. But this concentration they have provided is in molarity. So I have to use this equation, K2 divided by 1000 into molarity, which is equal to 0.025 10 raised to 2 into its molarity, that is 0.02. 0.02, which is equal to, I got the value like this. So the problem is solved. Next problem is the electrical resistance of a column of 0.05 molar NaOH solution of diameter 1 centimeter and length 50 centimeter. So resistance of a column of a concentration, NaOH solution concentration is given, diameter of the column is given, that is 1 centimeter, and length is given, that is 50 centimeter, is 5.55 into 10 raised to 3 ohm. Calculate its conductivity and molar conductivity. So resistance is given, I have to calculate conductivity and molar conductivity. What are the parameters given? Molarity is given, radius is given, that means diameter 1 centimeter, then radius is 0.5 centimeter, length is given 50 centimeter, and also resistance is given. We know that G star is equal to cell constant is equal to R into K. So from here K can be calculated, because G star, the information from R and L we can find out G star. So K is equal to G star by R. G star is nothing but L by A. So I substitute instead of G star L by A into R. L it is given 50 and R A is pi r square, because it's of a diameter, means column is having an area of cross section of pi r square, that is 3.14 into 0.5 square, and resistance is given here as 5.5 into 10 raised to 3, that is equal to, and I got kappa. If I got kappa, then I can find out lambda m. Lambda m is kappa divided by 10 raised to minus 3, because here the length, unit of length is given is in centimeter. So I have to use the equation or formula for centimeter, that is molarity into molarity divided by 1000, that is molarity into 10 raised to minus 3. So I have used the equation the problem is solved. Lambda m is determined. Okay, now we have learned new property, that is molar conductivity. What is the effect of concentration or dilution on conductivity and molar conductivity? In the case of conductivity, is for sure it is directly proportional to concentration. When you increase the concentration, conductivity increases. Why? In a unit volume, number of moles of electrolyte increases. When concentration is increasing, number of moles of electrolyte is increasing. So it is directly proportional to concentration. With respect to dilution, it is inversely proportional. If you increase the dilution, conductivity decreases. So directly proportional to concentration and inversely proportional to dilution. Reason is number of ions per unit volume increases, because conductivity is about unit volume. Okay. What about molar conductivity? Molar conductivity is directly proportional to dilution, that is inversely proportional to concentration. Directly proportional to dilution. Why? Because on dilution, volume containing 1 mole of ions increases, that is molar volume increases, and we have seen that lambda m is equal to kappa into V for 1 mole. Kappa into V for 1 mole. So lambda m proportional. When you increase the dilution, automatically volume of solution containing 1 mole of electrolyte increases. So lambda m increases. Is it clear? I hope it is very clear now. So two different or two opposite effect of concentrations on kappa and lambda m. Kappa increases with concentration because number of ions increases, whereas lambda m decreases with concentration or increases with dilution. Okay, so these are the two reasons. Let us see how lambda m behave with the dilution. Lambda m increases during dilution for strong electrolyte. This is what we saw in the previous slide. Lambda m increases with the dilution for strong electrolyte. I am plotting a graph in which root of C, that is, or you can say C raised to half, whichever the concentration, I am taking the root of that concentration value on the x-axis and lambda m on the y-axis, and I am trying to dilute the solution. So initially I have very high concentration, and at this particular concentration I try to check the molar conductivity, and it was that corresponds to the y-axis. I got an point here. Next I diluted, means concentration will reduce, so it will go in this direction. I diluted and there was a small increase in the value. Again diluted, again small increase, diluted, small increase. So it is increasing. Further I cannot see, because if you go like this, the concentration will become 0. So I try to connect them and I got a straight line. Very small dilutions, sometimes lambda m will show error. So I stop here. Now what I am doing is I will extrapolate, means I will keep a scale, keep a ruler and extend that line towards the y-axis, and on the y-axis it intercept. What does this mean? This intercept means it is lambda m at infinite dilution. Infinite dilution means at 0 concentration, almost 0 concentration. So lambda m will be maximum at this point, and it is known as lambda m0, or lambda m at infinite dilution is called as limiting molar conductivity, a new term, that is limiting molar conductivity, represented as lambda m0. 0 means at 0 concentration or infinite dilution. Okay, again, so lambda m, as I said, as we discussed in the last slide, it increases with dilution. Why? As we dilute, the molar volume increases, because as we dilute, the volume needed for 1 mole to occupy will increase. Hence, lambda m will increase. This is evident from this graph. You can see this is the graph of KCl electrolyte. It's a strong electrolyte. Strong electrolyte means when you add this electrolyte into water, it dissociates completely into ions. That's what meant by strong electrolyte. When you add electrolyte into water, it dissociates completely into water as K plus ions and Cl minus ions as cations and anions. So thus by dilution I am decreasing the concentration. That's what dilution is meant. I am adding water. I just add pure water into it or a solvent into it. By adding solvent, what happens? Molar volume increases and hence lambda m increases. And finally I am extrapolating, means I am using a ruler and extending this straight line to intersect y-axis. Y-axis, when it intersects, at that time the concentration is equal to 0 and it is called limiting molar conductivity. And it is the maximum value that you can get for lambda m. Limiting molar conductivity is the maximum value. So which is higher at a given point, lambda m or lambda m0? Lambda m0 will be higher. Lambda m at other concentrations can never go above beyond this value. Okay, what is the slope here? This is the slope. Slope means it's the inclination of the line, of the straight line or the plot obtained in a graph is a negative value, because as x value increases, slope is going down. So slope is a, we call the slope as a, and it is a negative slope because it is going down with the concentration. So it is a negative slope. If you have a straight line like this, then we can, as we know, there is a straight line equation that is equal to y is equal to mx plus c. Y means y-axis, m means m means slope, x means x-axis, and c is the intersect. So let's see what is the value of y, that is lambda m, what is the value of m, that is minus a, what is the value of c, and c is intersect is lambda m0. What is x? X is root of c or c raised to half. So if I substitute for that, lambda m for y, m the slope, that is minus a, x axis which represents the concentration, root of concentration, plus c is the intersect we call it as lambda m0 or limiting molar conductivity. If I rewrite it, I can write it like this: lambda m is equal to lambda m0 minus a c raised to half or root of c. There is a peculiarity for slope here. This slope minus a depends on nature of solvent, temperature, and electrolyte type. You should remember this electrolyte type. We will see this again after one more slide. In the next slide we will see a problem, and after that we will come back into this electrolyte type. So magnitude of A, this inclination or the slope value of that A depends on the electrolyte type. Next we will see a problem. Lambda m of KCl solution of different concentration 298 R. So there are different concentrations given here and its lambda m value is given. Show that a plot between, so I have to draw a graph between lambda m and c half as we saw in the last slide. Show that the plot between lambda m c half is a straight line. I have to draw the graph and substitute for this value and show that the plot is a straight line. Determine the values of lambda m0. Which was lambda m0? Lambda m0 is the y-intercept, the intercept on the y-axis. And A, what was A? A is the slope for KCl. So what I am doing is, first I have to find out C half, because it is C here, C half. I took the root of all these values and is substituted here against lambda m. So I am trying to plot it. So lambda m on the y-axis and on the x-axis it is C half. So I plot it and I try to find out the points here, and I draw a straight line, and this straight line intercepts at 150. So what is lambda m0? Lambda m0 is equal to 150 s centimeter square mole raised to minus 1. How can I find A then? Using this straight line equation. Lambda m is equal to this equation we saw in the last one, that is for your study. So lambda m is equal to lambda m0 minus a c raised to half. Then a is equal to, from this a is equal to, rearranging you will get this, substituting for this value 150 is lambda m0 minus 1. I took this one to find out a, 147 point lambda m, and its c half is 0.0315, and we get 92.67. So this is A. A depends on, as we said, temperature, electrolyte type and solvent. So electrolyte type, magnitude of A depends on electrolyte type. What does this mean? We have different types of electrolytes. You can see NaCl and KCl belongs to 1,1 type. MgCl2 and CaCl2 belongs to 2,1 type, and CaSO4 Mg 2,2 type. What does this type means? In the case of 1,1 type, let's look into 1,1 type. Na is in +1 and Cl is in -1. Similarly, K in +1, Cl -1. So if both the cations and anions are in oxidation state unity, if their oxidation state is unity, then it is called 1,1 type. Whereas in the case of 2,1 type, cation is in +1 and anion is in -1 oxidation state. It doesn't have nothing to do with the number, it is their oxidation state. So 2,1 means this is 2, you can call it as -1, so it's more easier to remember. So it is like 2, that is +2 and -1, and here it is 2 -2, or 2 type. 2 -2 type means +2 and -2. So these different types of electrolyte. In the case of 1,1 type, the value of A or the magnitude of A will always the same. So that means value of NaCl and KCl will be the same. That slope will be always the same for strong electrolyte. I am speaking about strong electrolyte. If it is a weak electrolyte, there is a different story that we will see in the next slide. So in the case of strong electrolyte, if for all the electrolyte of the type 1,1 will have the same value. So it's here, electrolyte of same type have same value of A in the same solvent. So NaCl and KCl in water will have same value of, that means they have the same slope or inclination in the graph that we saw there. And also for weak electrolyte, on the other hand, slope is not a straight line, so you cannot compare weak electrolyte here. For example, acetic acid is a weak electrolyte. You cannot compare with a strong electrolyte NaCl to find the slope. So far we have seen that slope is a straight line for a strong electrolyte. In the case of strong electrolyte like KCl, the slope we have already seen the last slide. Now we are going to see in the case of weak electrolyte. Again, I am trying to find out the values, lambda m values at different concentration, and I am trying to dilute the solution. So in a concentrated solution, I have a value here in the case of acetic acid. Then I diluted it, I moved the concentration, diluted it, and I found it here. There is a slight increase, then the increase started sharp. So the increase has become very sharp. So you can see slowly it started, then finally it went on very up. If I connect it, I will get it like this. That means this will not intercept y-axis. There is no y-intercept. Question is why? What happened? Why there is no straight line? Instead of that, I am getting a line like this. Because for weak electrolyte means, what is the definition for weak electrolyte? Weak electrolyte will not dissociate completely in a solution. So in higher concentration, dissociation will be very weak. As we dilute the solution, dissociation starts to increase, and at extreme dilutions, dissociation will be very fast. So this is case of weak electrolyte, and lambda m of weak electrolyte do not intercept y-axis on dilution. Why? Because for weak electrolyte, ionization means the tendency to ionize, which is represented as degree of dissociation. Degree of dissociation means how many molecules in 1 mole is dissociated. How many molecules in 1 mole is dissociated increases with dilution. Ionization increases with dilution. So what happens if ionization increases on high dilution? Lambda m increases sharply. Why? We were talking about molar volume. What was molar volume? Molar volume is the volume of 1 mole of electrolyte. So if I am taking acetic acid and adding it into water, I am taking acetic acid and adding into water, I am considering 1 mole of electrolyte, 1 mole of acetic acid. Then that is called molar volume. Doesn't matter whether it dissociated or undissociated. It is 1 mole of electrolyte. So if it is a concentrated solution, number of moles dissociated will be very less. And when I dilute, what happens? Volume increases. Molar volume increases. At the same time, number of moles dissociated inside it also increases. Volume increases, at the same time conductivity also increases. Why conductivity is increasing? Because the number of moles dissociating starts increasing. So molar volume means if I am diluting, then that means the molar volume is increasing sharply. At the same time, the number of moles inside that molar volume is also increasing. So that means the entire lambda m will sharply shoot up. Okay, so these are the two things. Now the question is how to find out lambda m0 of weak acid. Is it a way to find out lambda m0? Because using graph it is not possible. Using graph it is not possible because the dissociation is changing. When dissociation is changing, automatically all the parameters connected to it will change. So how to find out lambda m0 of a weak electrolyte? Is it possible? Yes, it is possible. But before that, we have to check a new law that make this possible, that make estimating of lambda m0 of weak electrolyte possible. I can calculate lambda m0 of weak electrolyte, but not using graph, but with an indirect method. To understand that indirect method, I should study a new law known as Kohlrausch Law of independent migration of ions. Kohlrausch's law or Kohlrausch Law of independent migration of ions. What does this law state? Limiting molar conductivity of an electrolyte. Again, limiting molar conductivity means the highest or maximum conductivity at infinite dilution. Maximum molar conductivity at infinite dilution, at 0 concentration. Limiting molar conductivity of an electrolyte can be represented as the sum of individual contributions of the anion and the cation of the electrolyte. So limiting molar conductivity of a electrolyte, I am considering electrolyte as NaCl, and its limiting molar conductivity is expressed like this: lambda m0 of NaCl is equal to the sum of individual. So NaCl is made up of 2 ions, which are the Na plus and Cl minus, and these individual ions have lambda m0 value, which is represented by lowercase lambda. This is uppercase lambda for the entire electrolyte, and the 5 ions it is lowercase lambda. Lowercase lambda 0 of Na plus and lowercase lambda m0 of 0 of Cl minus. If you add both these two, then you will get the entire lambda m0 of NaCl. This is what Kohlrausch found. How did he found this? Let us see with an example. So he took KCl and NaCl, and he drew that graph that we saw in the last slide, from where he got KCl value and he also got NaCl value. He used 2 electrolytes, and from one graph he got KCl value, and from the other graph he got NaCl value, that is lambda m0 value, and he saw the difference between KCl and NaCl, lambda M0 value, and the value was 23.4. The difference between lambda M0 was 23.4. Again, he took another two electrolyte, KBr and NABr. What is the difference between these two? In both cases, cation is the same. Only difference is the anion, isn't it? Again, he tried to find out the difference and he found that the difference is the same, 23.4. So, if that is the case, if both have the same difference, he deduced that I will split this KCl into 2, K plus and Cl minus, and this will also into 2, Na plus plus Cl minus. So, the difference when it comes here, it will be minus lambda 0 Na plus and minus Cl. So, he assumed that lambda M0 of KCl is due to lambda 0 of K plus and lambda 0 of Cl minus, and lambda M0 of NaCl is due to lambda 0 of Na plus and lambda 0 of Cl minus. So he substituted those values into this, and what happened here, Cl minus and Cl minus are cleared because of opposite signs. Then it is K plus plus Na plus, which is equal to 23.4. He did the same here. So he split KBr and K plus and Br minus, Na plus and Br minus, Br minus and Br plus, means minus and plus values will cancel out, and finally he got the value here. So he got both the same values. So these values he assumed is due to this thing. Why it is like this? Because they got the same value, because KCl value, lambda M0 of KCl, is contributed by individual ions. That's why he could work out like this and get the same value in both the cases. So he repeated this for several other electrolytes and he found similar results in all the cases. Thus he concluded and he put out a law called as Kohlrausch's law of independent migrating ions, which means that limiting molar conductivity of an electrode, for example KCl, can be represented as a sum of individual contribution of cation. Its lambda M0 is due to its ions lambda 0, that is K plus and Cl minus. Similar is the case with NaCl. For NaCl, its lambda M0 is due to lambda 0 of Na plus and lambda 0 of Cl minus. So in the earlier slide I said that we can use this to find lambda M0 of a weak electrolyte, isn't it? Kohlrausch law can be used to find. So how he used this to find out? Before that, we will see one application of Kohlrausch law. One application is to determine lambda M0 of an electrolyte. I can use lambda M0 of electrolyte from a list of lambda 0 of individual ions. So I have a list. For H plus, lambda 0 value is this. For Na plus, so for all the ions, lambda 0 is given in this table. And you are asked to calculate lambda M0 of CaCl2 and MgSO4. In the first case of CaCl2 dissociates to give Ca2 plus and 2Cl minus. That means there are total of 3 ions here. Lambda M0 of CaCl2, as he said, must be contributed by lambda 0 of CO2 plus and lambda 0 of 2Cl minus ions. That means lambda M0 of CaCl2 is due to lambda 0 of Ca2 plus and lambda Cl 0 of Cl minus, that is having 2 ions. So 2 into lambda 0 of Cl minus. I have the values of Ca2 plus here 119 and Cl minus here 76.3. I am just adding up. Lambda M0 of CaCl2 is equal to 119 plus 2Cl minus, that is 2 into 76.3, which is equal to 276. And he tried to make a graph and try to find out the original lambda 0 of CaCl2 from the graph, and he found the values are matching. That means his law can be applied to find out lambda M0 of an electrolyte using this table. Similarly for MgSO4 dissociates to give Mg2 plus and SO4 2 minus. Contributions, as he said, is due to Mg2 plus and SO4 2 minus. Lambda M0 of Mg is due to that of Mg2 plus and SO4 2 minus. From the table he substitute those values to here, that is 106 and 160. 106 of Mg2 plus and 160, and he found the value, and he matched this value from the experimental finding, and he found that both values are matching. So one of the application of Kohlrausch's law is to find lambda M0 of electrolyte. Without doing the experiment, you can determine lambda M0 if you have a table like this. This table again was created by him. Okay. Next is the application that we already mentioned, to derive lambda M0 of weak electrolyte. You can find the lambda M0 of this electrolyte from the table we have provided earlier. You can find this also from there. That's one application. But at the same time, Kohlrausch want to prove that that value that you get from the table is real, because you cannot prove it from a graph, because in the case of weak electrolyte it will never intercept y-axis. Then how can you prove it? So he tried to prove it in a different way. According to Kohlrausch's law, lambda M0 of this electrolyte is contributed by lambda 0 of CH3CO minus and lambda 0 of H plus. So because CH3COH dissociate to give CH3CO minus and H plus ions, isn't it? Now he selected, it has two ions like this, one positive and one negative ion. He selected an electrolyte, two electrolyte that has these ions in common. He selected one electrolyte, that is CH3CONA, where CH3CO is common to acetic acid. So this is a strong electrolyte. So he selected a strong electrolyte in which anion is common to that strong electrolyte, and he selected another electrolyte which is also a strong one, where cation is common to that is HCl. Now he now choose the two ions which is not common to this acetic acid inside these two electrolytes, that is Na from here and Cl. This is in this salt but not in the acetic acid. So he selected that Na and Cl, and it is NaCl. So he has now three strong electrolytes. One is sodium acetate, the other one is HCl, and the other one is NaCl. What is the peculiarity of sodium acetate? Sodium acetate has an ion common to acetic acid. HCl has a common ion to acetic acid, whereas NaCl has ions common to those two strong electrolytes but doesn't have the ions of acetic acid. Now what he did was, he did a calculation like this. Lambda M0 of CH3CO minus, he added its lambda M0 with HCl. Then he subtracted lambda M0 of NaCl. What happens? I am going to split. So as Kohlrausch said that this lambda M0 is a contribution of these two ions, and this is a contribution of these two ions, and this is contribution of NaCl. So I am substituting this Ca of this CO minus, this is a contribution of these two, CH3CO minus and Na plus, this is the contribution of H plus and Cl minus, and this is the contribution of Na plus, and since it is minus, both will get a minus charge. Now this Na plus and Na plus will cancel out, Cl minus and Cl minus will cancel out due to opposite charges. What will be remaining? It will be CH3CO, and what is it? It is lambda 0 of CH3COH. Thus he proved that by selecting these three, you can find their lambda M0 from using the graph, and you do this calculation. You will get lambda M0 from the graph, you will get lambda M0 from the graph, you will get lambda M0 because these are all strong electrolytes. You will also get it from the table. If you don't want to use, you can get it from the table, and it is exactly the same from what you're getting from the experimental data, if you are doing an experiment. So once you get this, you substitute, you will get a value, and that belongs to the lambda M0 of acetic acid. So lambda M0 of acetic acid is obtained. How? First I am choosing two electrolytes that is having common ion to acetic acid. Then I am choosing an electrolyte that is having common ion to that strong electrolyte but not to acetic acid. Then I am subtracting it. I am getting the value. So this is the second application of Kohlrausch law. There is still more application, but before that we will see one more problem. Suggest a way to determine lambda m0 value of water. So in the last one we have seen acetic acid as a weak electrolyte, and we have solved how to find out lambda m0. Here the weak electrolyte is water. Water has two ions, which are the H plus and OH minus. So what should I do? H plus, I am selecting one strong electrolyte that is having H plus, that is HCl. Then I have OH minus for water. Then I am choosing second electrolyte that is having OH minus, that is NaOH. So I have two ions, H plus and OH minus, that is common in water. And in this strong electrolyte there is two ions that is not common to water. They are Na plus and Cl minus, and I am subtracting that NaCl from this. So I will get lambda m0 of water. Again, one more example. Suggest a way to determine lambda m value of NH4OH. Let's see how. There are two ions, that is ammonium NH4 plus and OH minus. Can you suggest an electrolyte that is having NH4 plus Cl minus, that is an ammonium chloride. NH4Cl is an electrolyte that is having ammonium. Okay, ammonium chloride. Then an electrolyte with OH, you already selected here, that is NaOH. So you are adding ammonium chloride plus NaOH. So what is the electrolyte that is not present in ammonium chloride but present in both those two ammonium chloride and NaOH? Is again NaCl. So it is like this: ammonium chloride plus NaOH and minus and subtracting NaCl from it, that is lambda m0 of NaOH. Little more wider problem: lambda m0 of NaCl, HCl and sodium acetate. Ac means acetate. Sodium acetate are given here. Lambda m0 of these strong electrolytes are given here. Calculate lambda m0 of acetic acid. I have to calculate lambda m0 of acetic acid. So lambda m0 of strong electrolytes, and they are asked to calculate lambda m0 of acetic acid. So acetate ion, strong electrolyte corresponding to acetate ion is sodium acetate, plus one with strong acid is HCl. So I am adding the limiting molar conductivity of sodium acetate and HCl and minusing NaCl from it. So acetic acid is lambda m0 of acetic acid is lambda m0 of acetate plus lambda m0 of HCl minus lambda m0 of NaCl. This is common to this CH3CO minus, and this is common to H plus, and Na plus and Cl minus, which is not inside acetic acid, is subtracted from it, lambda m0 of NaCl. So I will get the value of lambda m0 of CH3COH. I hope it's clear now. So to the second application that we have seen, there is an addition. Using the second application, you can also find degree of dissociation alpha and equilibrium constant from the derived lambda m0 of weak electrolyte. Degree of dissociation is important for weak electrolyte, not for strong electrolyte, because for strong electrolyte degree of dissociation is 1 in dilute solutions, whereas for weak electrolyte degree of dissociation is not 1. In acetic acid, for example, out of 100 only 5 molecules will be dissociated in water at normal concentrations. Again, out of 100 molecules, only 5 molecules on an average, only 5 molecules will be dissociated in water. Then what is its degree of dissociation? Its degree of dissociation is 0.05. That means 1 divided by so what you have to do, 5 divided by, so what you have to do, out of when you calculate, so how to calculate alpha, degree of dissociation? Degree of dissociation can be calculated by the number of molecules dissociated divided by total number of molecules. So as I said, out of 100 only 5 molecules will be dissociated. So that is 5 divided by 100. What is the value? 0.05. So degree of dissociation in the case of acetic acid is 0.05. 5% will be dissociated, 95% will be in the undissociated form. Okay, so this is called degree of dissociation. And equilibrium constant can be derived from lambda m0 of a weak electrolyte. Let's see how. Degree of dissociation of a weak electrolyte in the terms of lambda m is given like this. Degree of dissociation is equal to alpha into lambda m divided by lambda m0. Molar conductivity divided by limiting molar conductivity. Alpha should be always a fraction. At most for a strong electrolyte can be 1. It can be 1. Whereas for a weak electrolyte it is always less than 1. For it to be a fraction, then you have to subtract you have to divide on the numerator should be a small number and the denominator should be high number. This is how you can remember it. Alpha is equal to molar conductivity divided by limiting, because limiting molar conductivity is the maximum value, is having the maximum molar conductivity. So lower value on the top and in the numerator and the higher value in the denominator. So the value of alpha will be a fraction. Alpha is equal to lambda m divided by lambda m0. And we have seen an equation in class 11 that is connecting Kc and alpha for an electrolyte of the type 1,1. That means electrolyte that dissociate to give 1 cation and 1 anion. Kc value will be Kc value is C alpha square divided by 1 minus alpha. What is C? C is the initial concentration. This is not the C in the equation that we saw for lambda m. Kappa divided by C. It is not that C, it is molarity. This C represents molarity. So molarity into degree of dissociation square divided by 1 minus degree of dissociation. So this is this equation is applicable only for the electrolyte type of 1,1. In the other case, in the electrolyte for other types, the equation will vary. So as far as +2 board exams are concerned, this equation is only for you to study. So Kc is equal to C alpha square minus 1 minus alpha. So instead of alpha I can put lambda m divided by lambda m0. Molar conductivity divided by limiting molar conductivity. Then if I substitute, I will get an equation like this. In most cases you have to find out alpha, then you can substitute alpha here and you can find out Kc. So this is the equation to study for Kc. C into lambda m square divided by lambda m into lambda m0 minus lambda m. This is the equation that you have to study. And in the case of 1,1 type, Kc will be, the unit of Kc will be mole per liter. Unit of Kc is generally not that important, but here in this case, since you are getting alpha and there is only one concentration term here in molarity, all others are fractions without unit. So you can write the unit of this Kc as mole per liter. Let's see a problem. Conductivity of concentration C, small c, mole per liter is given for the acetic acid. Its conductivity is given as 4.97 10 raised to minus 7 and limiting molar conductivity is also given. Calculate its dissociation constant. So I have to calculate Kc value. What are given? Conductivity is given. Let's see, conductivity is given, initial concentration is given. Instead of value, this one I have given like this, 1.7 10 raised to minus 3 is the same value. Limiting molar conductivity is given. I have to find out dissociation constant. So dissociation constant Kc it is given, since it is an acetic acid 1,1 type, it is C alpha square divided by 1 minus alpha. So for that I should know alpha. Alpha is lambda m divided by lambda m0. For that I should know lambda. Lambda is not given. Lambda m is equal to kappa divided by, since the unit is in centimeter, the formula used must be like this: kappa divided by 10 raised to minus 3 into molarity. Molarity, kappa, all are given. Substitute it. I will find out lambda m. And using lambda m, I can substitute into this equation for finding alpha. Alpha is equal to lambda m divided by lambda m0. Lambda m divided by lambda m0. And I have got the value of alpha, which is a fraction. And from this, using this, I can go for Kc value. C alpha square. C is given, that is this one, into alpha square of the alpha value we got here, 1 minus alpha, and I could see Kc value. Pause the video and try to do it by yourself and see. Now the next question: molar conductivity of 0.025 molar methanoic acid. This is methanoic acid, and acetic acid is ethanoic acid. So for methanoic acids, its concentration is given, its molar conductivity lambda m is given. I have to calculate Kc value and alpha. Lambda m0 is not given, but they have provided the values of cation and anion. So molarity is given, lambda m given. They have provided molarities of ions, means I can calculate lambda m0 using Kohlrausch law. So it is like this: value of this one is given here, it is given here, which will be equal to, so lambda m0 is the addition product of this one. So this is C lambda m m0. Alpha is lambda m divided by lambda m0. I calculate and I got the value of alpha, and from this I can calculate Kc. Kc is equal to C alpha square 1 minus alpha. Substituting the value, I get the value. And you have to write the unit, because there is only one concentration term here, and that concentration in the equation, concentration term is mole per liter. Generally for Kc value, you are not supposed to write the you don't have to write the unit, but in this case, since it is very clear there is only one C, the unit must be mole per liter. It's always convenient to write. Finally, we are going to selfie questions. A solution occupy a volume of 5, so the unit volume is given 5 centimeter cube of a container, and contains 5 mole of electrolyte. So the number of moles and volume is given. Its conductivity is 0.25 centimeter raised to minus 1. Conductivity is also given. Calculate its molar conductivity. Read all the questions. Try to find out the answer. Once you find out the answer, come back and evaluate. So if it is a statement type of question, we will not provide the answer. You have to find it from the textbook or from the video here itself. Otherwise, we will try to find out. So let's discuss again. Solution contain volume of 5 centimeter cube of a container. That means volume is given, number of moles is given, conductivity is given. So what is the equation for molar conductivity? Is K by C, or K into N by V, or K into V by N. These are the equations we already saw. Just substitute the values. Conductivity is given, number of moles, volume is given, number of moles is given. So the unit has to be careful, because it's centimeter, then Siemens, centimeter square, mole raised to minus 1. Next is define conductivity and molar conductivity for a solution of an electrolyte. This is a statement equation. You can search and find out. Conductivity is the conductance of unit volume. Molar conductivity is conductivity of molar volume. That's the difference. Conductivity, conductance of unit volume, whereas molar conductivity is conductivity of conductance or conductivity of molar volume, 1 mole of electrolyte. What is the effect of dilution on conductivity and molar conductivity of an electrolyte? What is the effect? Conductivity decreases with increase in dilution, because number of ions is decreasing. Molar conductivity increases. Why? They have not asked for the reason, but just it's interesting to answer. When you answer something, it's always interesting to find a reason for that. Then it is easy for you to grasp. Molar conductivity increases with dilution. Why? With dilution, molar volume increases. So it depends on molar volume, hence K decreases and lambda m increases with dilution. Next is a similar question that we saw in the last slide. Conductivity of acetic acid is given. Its C is given. Calculate its molar conductivity. You have to calculate molar conductivity. Lambda m is given. M0 is given. Means limiting molar conductivity is given. What is Kc value? So C is given. Conductivity is given. Lambda m0 is also given. Lambda m is, since the unit is centimeter, I have to use K into 10 raised to minus 3 into C, molarity. This is molarity value, and finally I will get the value like this. Okay.